Okay, so the question that you were asking was that if you have data from the Economic Survey of India, you have data on savings from 1951 to 2015, you have data on the disposable personal income from 1951 to 2015, you do a regression where savings is a dependent variable and the DPI is the independent variable. You get a value for beta. Beta is the marginal propensity to save. But obviously along with beta hat, you'll also get an estimate for the standard error of beta hat, the t values and all that. What does the standard error mean? It gives you an estimate of what are the various values of beta that beta hat can take if you use different samples. Right? But do you think this is a problem in this context? It is, no? Because you see, if you are doing a cross section, if you are taking a sample of size 100 for X and a size 100 of Y, you get beta hat. If you pick up another 100 people and take X and Y, you get another beta hat. If you take another set of 100 people randomly, you get another beta hat. Right, and that's the whole idea, where beta hat will have a spread, and in a single equation, the variance of beta hat essentially gives you what that spread would be. Now, what is the data that you used? You used all the data of India's GDP that is available to you from 1951 to 2015, all the data on India's savings that is available to you from 1950 to 2015. So, can there be another sample? Can there be another sample or can there not be another sample? There cannot be another sample? So, what is that beta hat doing? What is that standard error of beta hat doing there? Because if the standard beta hat is supposed to give you a sense of variability of beta hat across different samples, and in this case, as you guys say, there cannot be another sample, what does that standard error of beta hat mean there? You see, time series data is an important question. That is going to give a very important entry point into the discussion.
Even if there is no another sample, beta will vary across different time intervals.
No, we are using the data for the whole set. Right, so it's not a question of beta varying over different time intervals.
There is no another means variability beta is 0.
Yeah, so what is the standard error doing there? You see, you have to understand that time series is a fundamental thing. What do you have? You have the data on GDP from 1951, say so many crore rupees, GDP in 1952, so many crore rupees, GDP in 1953, so many crore rupees, savings in 1951, so many crore rupees, savings in 1952, so many crore rupees. That's the data that you have. And you are saying that that's all the data that you have, which is only partly true. Because the value that you are seeing in 1951 of GDP is not the only value that could potentially have been. If you consider the value of the GDP in 1951 as a random variable following a probability distribution, and the one value that you have seen is one realization of that random variable, then you will see that in fact many different samples are possible and you have observed one. You see this very important point, that the value of GDP that you have got in 1951 is one value of among many that could have been potentially generated by some underlying probability distribution. Right? If I say, for example, that the time taken for you to come to Kalina campus today from your home was 23 minutes, there is actually an underlying probability distribution which is generating many values. You have seen one such value. Right? So the time taken for you to come to the Kalina campus today is actually a random variable which takes different values with different probabilities. You have seen one particular realization there. Right? Sure? So tomorrow's value, assuming this underlying probability distribution is unchanged, tomorrow's value is another realization of this random variable. Day after tomorrow's value is another realization of this random variable which follows a probability distribution. So in effect, what you have, the data that you have of DPI from 1950 to 2015 and the savings from 1950 to 2015, 1950 to 2015 is just one possible realization of many possible samples that could have been. You see the point? Sure? Everybody gets this? This is a very, very important point, because that is going to lead us to a next important point. Is everybody clear? So there is a probability distribution of GDP in 1951. The one value that you have seen is one possible realization of this value. The value of GDP that you get in 1952 is a random variable which is a probability distribution. The one value that you see is one realization of these values. Right? Similarly for 53, 54, 55 and so on. Sure. Now, so what we need to now say carefully about, is to think carefully about the underlying probability distribution which generates all these values. Okay? A very strong assumption would be to say that this underlying probability distribution, there is a probability distribution for 1951, there are probability distribution for 1952, there are probability distribution for 1953, 54, 55, 56, etc. Right? And if you are assuming that this entire probability distribution is unchanged over time, suppose you are going to assume that this underlying probability distribution is unchanged over time. So its mean is constant, its variance is constant, its skewness is constant, its kurtosis is constant, its correlations across, etc. Everything is constant, right? What you are assuming is something which is very, very crucial in time series modeling, what is called strong stationarity. Okay, so we say that a random variable xt, t goes from 1 to t, is strongly stationary if the entire joint distribution of xt, right? You have got x1, you have got x2, you have got x3, you have got x4. These are all jointly distributed random variables. If the entire joint distribution is unchanged in time, you have what we call strong stationarity. Now, all of you will agree that strong stationarity is too strong and a very strong and an unrealistic assumption. Right? Over the years, many changes take place in the economy. And it is unlikely that strong stationarity will be actually met with in practice. Is this clear? The idea of strong stationarity clear to everybody?
Could you please repeat the definitions?
Essentially what we are saying is, if you think of xt now as a random variable, which takes a value in x1, x2, x3, x4, x5, etc. So if you assume that the entire joint distribution of x1, x2, x3, x4 is unchanged in time, its mean is constant, variance is constant, covariance are constant, higher moments are all constant, unchanged in time, you have what is called strong stationarity or stationarity in the strict sense. Okay? But in reality, you don't really need such a strong definition. You can often work with a slightly weaker definition. That definition is called weak sense stationarity. And that's going to be the more relevant definition for us. So, stationarity in the weak sense. Weak sense stationary. Or simply stationary. When I say stationary in the future, it will really mean weak sense stationary. If you think of a random variable xt is weak sense stationary or simply stationary if the following three conditions are satisfied. Okay? You don't need to write this down now, that's there, and this recording is working now fine. So pay attention. Okay? If so if mean of xt is constant, okay, b is constant and finite, right? Or really say, let's put it even better, is a well-defined constant. And finally,